How's it going, everybody? So we're going to be talking about the properties of polynomial functions. The idea behind this is we're going to explore parts of the polynomial that we are interested in, such as x-intercepts, y-intercepts, maximum and minimums, when the function is increasing and decreasing, as well as domain and range. Now, a lot of these topics we have already talked about before. Now, finding the maximum and minimum values within a specific domain is going to be the only difference, and we'll of course make sure we highlight those ideas. Now, for this first one, it says given f of x, find the following information. This graph was graphed on Desmos, and you will need the function. You don't need to graph this function. It's not really all that important. The idea is being able to look at this function and get all the information out of it. So let's just go ahead and do that. So first and foremost, the domain of this function, we interpret domain from left to right. So left to right. Now the idea, guys, is when we read left to right, we're looking for instances where the graph is being restricted. It's not allowed to go left or go right. Does it have a break? Does it have a stop? And you'll notice, even though there's not an arrow posted at each end, we should understand that this graph is continuing to go to the left and up, and this graph is continuing to go down, but also to the right. Now, if it's going to the left and it's going to the right without anything restricting it, we tell ourselves that that is a negative infinity as you go to the left and positive infinity as you go to the right, okay? So just be aware of the domain being from negative infinity to positive infinity. Now, there was a couple of ways that we described that when we learned about, the different notations. For instance, you've got like your interval notation, your set builder notation. For this right here, you could say that it is from negative infinity to positive infinity. That's interval notation. Remember, infinities don't get brackets because you can't contain or, touch infinity, right? And if you wanted to do set builder notation, you would have done something like x is such that x is an element of the all real number system. Both would have been sufficient if you wanted to, okay? Now the y's, we read it from bottom, right, to top, okay? So from bottom to top. And so looking at this right here, we notice that the graph is going up, like we said, and down without anything restricting it. Just because the picture right here ends here and here, that doesn't mean the graph ends there. That's just the snippet that we got from the Desmos. But if you were to keep expanding, you'd see that that graph would indeed keep going. So we would have it going from negative infinity, because that's going down, negative infinity, to the top, which is towards positive infinity. Now, once again, you could have said, y is such that y is an element of the all real number system. And that would have also been, been able to explain the range. Now, moving on though, the y-intercept is basically wherever it crosses the y-axis. You'll notice it only crosses the y-axis at one instance right here, okay? And that was not my highlighter. There we go. At 0, negative 1. So we would put that information here. So 0, negative 1. And for the x-intercepts, there's actually quite a few, and we're going to have to make sure we document them all. So we've got ourselves one here, we've got one here, and we've got one here, because that's where it crosses. Now, they're not pretty numbers, and for some odd reason, a lot of students, they get kind of nervous when they see, x-intercepts that don't have pretty numbers. That's okay. We got to get more and more comfortable with x-intercepts not being a pretty whole number, okay? They might be decimals, and that doesn't mean you're wrong, okay? You very well could indeed be right. So for this right here, you would say negative 0.532, 0. You would have 0.653, 0, and you would have 2.879, 0, okay? So you'd have 3 x-intercepts. Now, it goes on to ask this next question, find the maximum on the interval of 1 to 3. So 1 to 3, that's talking about domain. So it's saying from the number 1, which is located right here, 2, 3, What is the maximum? Maximum meaning the highest point. Now you could also draw little dots like this, okay? And like so. So basically in between these two green lines right here, what's the highest point? And so the idea is you're looking inside of here, okay? Well, conveniently, the highest point is this right here. Let me try to use this color, right? At 2, 3, okay? It's the highest the graph can get for the y. So we would say the maximum is 2, 3. Now, to find the minimum, so this is kind of switching gears now, okay? And let me kind of clean this up a little bit. So that way it's, we're not having too much going on. We're finding the minimum between -1 and 1. So I'm going to once again kind of highlight the key features that we're looking at. And the key features we're looking at are -1 to 1. And let me draw the lines to kind of give you a better representation. So here and here. And so this little piece right here, we're looking inside of here. Now the minimum means the lowest point on the graph, so the lowest value of y. And hopefully that's a little easy to see. It's this right here, this y-intercept. So your y-intercept can also be a minimum. So just because it has one, title doesn't mean it can't have another title. So this is both a y-intercept and a minimum. So someone could easily ask a question, is the y-intercept also a minimum of the polynomial function between -1 and 1? And you could write either true or false. You could easily, ask a question like that. So this right here is at 0, -1. And there we go. Now let me go ahead and clean this up again for the next problem. So the next one wants us to do 2, 3. So between 2 and 3, okay, what is the minimum? Okay, so that's interesting. So let me go ahead and draw my lines here and here. So I'm interested, and maybe I should keep going so you can see a little bit better, about this wedge right here, okay? Now, the lowest point, okay, between this wedge is actually located right here, okay? Because that is the lowest point before it then crosses, and then this red part, this little leg sticking out, is outside the green barrier. So this right here, guys, is right on top of it, and it looks like it's at -1 or 3, -1. So this would be 3, -1. And so as you can see, a minimum is not always going to be one of these little humps, one of these little valleys, or one of these mountains. Sometimes your minimum or your maximum can vary depending upon what little wedge you're looking at, okay? So just be aware, don't get so hyper-focused on just these when you're asked to look in between a specific spot in the domain, okay? Just be aware of that, okay? Now, let's go ahead and talk about where the domain is increasing and the domain is decreasing. Alrighty, so now when we are talking about increasing and decreasing, we actually will be focusing on the valleys and the hills. So believe it or not, these spots right here are what help us with increasing and decreasing. And so when we go ahead and look at them, it's always good to just kind of highlight them, because those are numbers you're going to be utilizing in your descriptions. And we describe it using domain because it's easy to tell when a function is decreasing left to right versus up and down. You can ask me later on in life why it doesn't work. I'll kind of show you, but for the sake of this video, I don't want to make it any longer or overcomplicate it. But it's the only way we can really describe increasing and decreasing of a function is when we move from left to right. Now, the way we start off figuring out, how do we begin that process, I always like to say, I like to put like my pencil at the very far left of the graph, and I begin to trace. And if you'll notice, as I begin to trace this graph, hopefully you came to the realization that my, red mark was going down. Hopefully you were able to kind of see that this was a downward draw, right? As I began to trace this, okay, it went down. But as soon as I hit 0 right here, okay, you'll notice I then stop decreasing. I stop going down, and then I begin this process of going up, and I do this, okay? And you'll notice as I begin to draw, I mean, I'm clearly going up as I'm drawing, right? And then I hit this 2, okay, for the domain, and I once again begin the process of drawing down, okay? So here, I'm decreasing in 2 spots, and only in one instance, I'm increasing, okay? Now that can flip on its head depending on the function, but as long as you trace it from left to right, it will always ensure that you've got the right, increasing and decreasing, okay? So when looking at this right here, the way I would describe it is using domain. I would say from negative infinity to the value of 0, I am decreasing, okay? And then after I pass 0, I then start to increase. Now you'll notice I didn't put a bracket at 0 because at that particular valley, when the arrow starts making a turn, there's a point in time where the arrow is actually just pointing straight as it begins to make that change to being decreased to increase. So in that instance, it's not doing either. It's not increasing, it's not decreasing. It's purely just going straight. So I gotta say, I can't include it, so that's why I have a parenthesis. And which now then leads me to now talk about how it's going. I go ahead and make that adjustment, okay, beyond that point. So let's go ahead and now say from 0 onward to 2, I'm going to be going up. So from this value of 0 all the way to the value of 2, going up. But once again, when you hit that hill, he's going straight for a moment, which means I can't include it at 2 because he's making the shift to now going down. And so from 2 to infinity, I'm now going to be going down, okay? So that right there is how you would describe your increasing and decreasing. And this is something we have talked about a long time ago, but hopefully this is a good refresher. Now let's go ahead, let's talk about this one, but a little bit more, I guess, a little bit quicker because we kind of talked about it already. So once again, looking at this graph, it does have a domain from negative infinity to positive infinity because it's not being restricted. Same thing with the range from negative infinity, positive infinity. The y-intercept, I notice, is right here at 0, 4. So I have 0, 4, okay? Then the x-intercepts are right here and right there. Yeah, it's just that. So it is going to be at negative 1.053, 0 for my x-intercept. There's only one. Now let's talk about the maximum and the minimum. So the idea is from 0, so here to 3 to here, what is the maximum? Well, that's a little easy because it's the hill right here. So this little spot tells us that we have a maximum at 4.742. So I would say at 0.792, 4.742, okay? Then after that, we're going to find the maximum between 0 and 6. So 0 is right here. 6 is over here. So the maximum there, okay, between those two, it used to be, and I would agree that it looks very close, it used to be here, but you'll notice there's actually a point up here that's higher than that dashed line where that maximum used to be. And so it looks like at that point we have it at 6,5. That is my new maximum. Remember, when looking at the interval of a domain for maximum or minimum, don't focus on just the hills and the valleys. Look at what the biggest, the highest possible point could be. Now, the next question says maximum, but we're going to scratch that out. Let's pretend it says minimum. And so we're now going to find the minimum between 0 and 6, and that one's an easier thing to verify. It's right here. It's at 4.208, comma 0.758. Okay, and so that right there would be the minimum between over that interval. Okay, so now let's talk about where its domain is increasing and decreasing. Alrighty, so I went ahead and highlighted the important parts, which is the hills and the valleys that tell us, the turning points. Another description is people like to call these turning points, where the graph turns from decreasing to increasing. So you could have that as a good vocab word to remember. Those are turning points. Now, we always start on the left, move our way right to tell how it's, moving up or down. So here, I'm going up clearly, right? And so as I make my way all the way up from negative infinity to 0.792, I'm increasing. So I'm going to put that there. So negative infinity to 0.792. And so I'm going to go ahead and now notice that I switch and I start moving down, right? So I'm going down, so I'm decreasing, starting at the 0.792 to the next value of x, which is my 4.208. But then I quickly make a shift back to increasing. So just be aware that you have two instances of that. So you have from 4.208 comma infinity. There we go. Back to normal. So there you go. That's how you do that in a nutshell. Now let's talk about one more thing. We have some multiplicity and end behavior that we need to talk about, and then we're done. Alrighty, so for this right here, guys, this is talking about core concepts of end behavior of polynomials. So you'll notice here that it talks about this thing called degree and leading coefficient in bold. The idea is that when it says that you have a degree that's odd, that's saying something like x to the third, x to the fifth, x to the seventh, or to the ninth. Why say odd? Because these degrees are odd numbers. Okay, so that's what it means. Now the leading coefficient being positive, that means say you had a x to the third plus an x squared plus 5. The leading coefficient, the x cubed, it's a positive 1, so because it's positive 1, the end behaviors are going to have one arrow going up and to the right, and then down and to the left. And that's always going to be the case. Like, you can guarantee that the end behavior will behave that way if you have a odd degree with a positive leading coefficient. Now, if the tables turn and it's a negative leading coefficient, one to the right, it could look something like this, like a negative 2x to the fifth plus x cubed plus x squared, something like that. You still have an odd degree because it's to the fifth power. Okay, that's the leading degree. And then the end behaviors change due to the fact that there's a negative here. Okay, so what that goes ahead and tells us is that we have one arrow going up and to the left now, and then one going down and to the right. So basically they switch, okay? Now, something to make a special note of, and let me go ahead and kind of erase this and get this out of our way, is you'll notice it says f of x goes to infinity, that whole thing right here. And just to highlight it, maybe it's easier to see this stuff right here. This is referencing y and x. So it's trying to help you tell your domain. So the idea is that f of x, remember, is a fancy way of saying y. So you could easily write y goes to infinity or y goes to negative infinity. So anytime you see x, f of x, you can just write y instead if that helps. So if that's the case, then if I were to say what is my range for something like this, it's going to be from negative infinity, because you read it from bottom to top, to positive infinity, because I utilize this and then this. And then my domain, you read it from left to right. So the furthest to the left is the negative infinity, so you write that first, to positive infinity, okay, because you write that second. And you can say the same thing for this first one over here that we did, okay, and kind of getting rid of all the craziness right here. We said that, the range for this, you read it from bottom to top. So all you would have to do is just look at the bottom one to the top one. You'll notice it's the same. And then the domain, you read from left to right, so you'd have from left to right. Okay? So there you go. It really helps. It's really helpful when writing, domain and range, when you just know the end behaviors. Okay? Now, the even, when it says a degree is even, that's something like if you have x squared, x to the 4th, x to the 6th, x to the 8th, even numbered degrees, okay? Now, positive meaning it's the leading number, okay, with the highest degree is positive, so you'll have your end behaviors for evens both be going up, but if it's negative, they'll be going down, okay? So we'll be able to kind of illustrate that with some of the examples over here. So this right here is describing a polynomial, okay, but in a fully factored form, okay? So if we're looking at number 3 right here, it has our leading coefficient, if you'll observe, is positive, okay? There's no negative right there. So since it's positive, okay, I'm going to circle, hey, it's positive, okay, that's good piece of information. And it goes on to say, is it a degree that's even or odd? Well, in order to understand if it's even or odd, you have to count the powers and add them all up. So the idea is that this right here is a power of 2. These right here, they didn't have degrees explicitly written because they're just ones. Okay, they're just 1. So if I did your 2 plus 1 plus 1, well, that's going to go ahead and give me a power of 4. This means my function is going to be an even function, and so we would go ahead and circle this right here, even. Now, the different x-intercepts come from the factors. So the first one, x plus 1, is a minus 1. Then the x minus 1 is a plus 1. And then the x minus 3 is a plus 3. The multiplicity comes from the exponent attached to the factor. So for the x plus 1, that would be there's 2 of them. For the minus 1, there's 1. For the minus 3, there's 1. And that's because they had degrees of 1. Now, this is helpful because if you end up with an even multiplicity, that means your graph is going to bounce. And so here, this would indicate that we would bounce. And if it's odd, it's going to cross. So, of course, the other one would cross. Now, what does that essentially mean? So let's take a look at it over here. So I'm going to put in my x-intercepts. And that's going to give me a -1 right here, a 1, and a 3. Now, because we know our even and positive leading coefficients, that means since it's even, it's going to go up and up. And it's a matter of us figuring out, how is it going to interact with the x-intercepts? Well, at -1, we said it bounces, so it'll bounce, and that's what it means by bounces. It'll touch and then come back up. And then it'll come back around and cross through 1, cross through 3. So as you can say, it'll cross and cross, creating our even shape here. Now, as far as the end behavior is concerned, when we're talking end behavior, we're talking this right here and this right here. So for the one on the left, as it goes to negative infinity, he's going up towards positive infinity. And as x goes towards positive infinity here, he's also going up towards positive infinity again. So the end behavior can also be seen if you were to look back at this chart over here. You could have easily seen the answers where as x goes to negative infinity, f of x goes to positive infinity, helping you with the domain and the range. Now let's talk about number 4 here. So here, once again, we can count the degree by looking purely at these right here. So 4 plus 2 plus 3. Well, 4 plus 2 is 6. 6 plus 3 is 9. So this indicates to me that I have an odd degree. And then in addition to, my leading coefficient is negative due to the negative right here. Okay, so that's going to be helpful when we go to create our picture. Now the x-intercepts are at 5, -2, +3. The multiplicity is the degree of the factor, so there's 4 of these, 2 of these, and 3 of these. Now, because right here I've got myself a 4, that means it's going to bounce here again, but then cross right here, okay? So let's be aware of that as we begin to put in our picture. So I've got myself a -2, 3, and 5. Put in my dots. And since my coefficient was negative and my degree was odd, that means my end behavior will do something like this. It'll have an arrow going this way and an arrow going this way, okay? So as we begin to draw, we have a bounce at -2. It's going to go ahead and cross at 3, come back, bounce at 5, and then come back down. And it will connect with the other arrow at the end. So that's how it would look in terms of our picture. Now, as x goes to -infinity, f of x goes to +infinity. And as x goes to +infinity, y goes to -infinity. And that right there, ladies and gentlemen, is multiplicity interacting with the different functions of the quartic and of the cubic. And so now you're kind of getting a glimpse of, how we can not only graph these, but how the end behaviors can help us understand more about the graph and how it interacts. And so guys, that's it for this video. Let me know if you have any questions. Thanks, guys.